Hello everyone, welcome to my videos on elementary differential equations. This is video number 12 for chapter 5. The topic for the chapter is the Laplace transform. In the previous video, we talked about the step function and the piecewise continuous function, and representing piecewise continuous function with the step function. And then we also talked about the second shift theorem. Okay, so in this video, we'll discuss how to perform Laplace transform for piecewise continuous function, utilizing mainly the second shift theorem. So we'll go through examples. In the examples, we will compute Laplace transforms for given piecewise continuous functions. Okay, so let's recall the second shift theorem. It says that for a function f of t, if its Laplace transform is capital F of s, then the shifted function uct times ft minus c, the Laplace transform of that is the Laplace transform of the f, the unshifted function, times an exponential e to the negative cs, okay, where the c here is exactly the amount that you shift. Then this can be written equivalently as that the inverse transform of this guy here is this function per our definition. Okay, so let's look at some examples. Okay, so here is a piecewise continuous function, f of t equal to sine t on the interval t between 0 and pi over 4. And then for t bigger than pi over 4, it's sine t plus cosine t minus pi over 4. Okay. The first step towards finding the Laplace transform of this is to rewrite this in terms of unit step function as we discussed in the previous video. So we follow the algorithm or the guideline we had. So look at the first piece. We take the function, which is sine t. Then it's multiplied by what picks up this interval. So here would be 1 minus u pi over 4 of t. And then plus the second piece is this function, sine plus cosine. We copy it down here. And then this is multiplied by what picks up this interval, which is u pi over 4t. Okay? And then we will look for simplifications. We would like to combine these terms together. We would think the step functions, we would take them out, put them together. Okay, and now we can collect terms with the step function. So sine t times 1 is by itself, and then for the step function, you will have a negative sine t and all this. If you add the negative sine t here, it cancels the sine t, and you only get the cosine here. That's therefore we have this expression. And now I would like to explain a equivalent algorithm, but a bit different, maybe more convenient to use here. So you can do the following. So if a function is piecewise continuous and defined in the interval starting from 0 and for t growing, like which is written here, then you can do the following. Then you can start from the first function, which will be just there. Then you look for the next t value where it's discontinuous. So here will be pi over 4. And then you add the step function starting from there, u of pi over 4t. And then this is multiplied by the difference between this function and the previous one. So it will be this minus that, and where the sine t would cancel, and then you have just cosine, and that's what you get here. Okay, so that's probably a quicker way of reaching to this expression. Okay, so now we can take Laplace transform of our function f. So by linearity, you take Laplace transform of the sine and the Laplace transform of this function here. Okay. So Laplace transform of sine we already know, and then it's this Laplace transform which we need to look at. So this fortunately is exactly written as a shift function. So it's written as the shift of, let me write. Okay, so this function can be written as u of c of t times a function g of t minus c, where c is pi over 4, and the g as a function of t, the original unshifted one, is cosine t. Okay, so we shall be able to recognize that, and then we can apply the shift theorem, and we would take the Laplace transform of cosine and then multiply with the e to the negative cs, where c is pi over 4. Okay? Okay, so therefore we reach our answer. So Laplace transform sine is 1 over s squared plus 1, and Laplace transform of this shifted function is the transform of cosine, which is s over s squared plus 1, times this exponential function caused by the shift, so negative pi over 4s. Okay, so the important thing is to recognize the unshifted function from this expression. This is shifted, therefore in the unshifted one you have to shift this back into the independent variable. Okay, so don't worry, we'll have a few more examples. Okay, so here's our next example. Function f of t is defined on the interval 0 to 1 is t, and on the interval t bigger than 1 is constant 1. So we can sketch the graph of this function, and it's rather simple. So this is f of t, and this is t from 0 to 1. It's t, so it's 0 to 1 here, and then when t is bigger than 1 is constant 1. So we see the function is actually continuous, but it's defined in a piecewise way, and just as is, without using any tricks, we to compute the Laplace transform, we'll have to throw in the definition, which would involve quite some work. So let's see if we can use the second shift theorem to help with the computation. Okay, so let's rewrite the function using unit step functions, as we have learned. So the first is t times the interval that picks up the from 0 to 1, so 1 minus u1 of t. Okay, and then the second is 1 times this interval. It's being picked up by u1 of t. And then we see we'll have also can use the other way. We can think it's t here, and then you will get u1 of t times 1 minus t. So if I write t minus 1, I get a negative sign. And then this can also be obtained directly from manipulating this here. Okay, so let's take the Laplace transform. Then we see that the transform of t minus the transform of this shifted function. So let's write out again what will be this shifted function if we think this is an uc of t times g of t minus c. So we see clearly c is 1. So what is g of unshifted? Well, then you have to take the t minus c, which is t minus 1 here, and write it as t, right? Shift it back. So g of t is t. Okay. And therefore, the Laplace transform of this second term will be the Laplace transform of this function here, multiplied by the exponential. e to the negative cs, and where c is 1. Okay, and then we can put it in. So Laplace transform of t is 1 over s squared minus Laplace transform of that is first the shift e to the negative s, and then the Laplace transform of t again is 1 over s squared. Okay, so here's another example by applying the shift theorem, and this is a simple example because after manipulation from this form you can easily figure out the unshifted function. Okay, let's look at our third example. It's the following. The function is 0 for t less than 2 and is t plus 3 for t bigger than 2. So this can be easily rewritten in using the step function t plus 3 times what picks up here, which is u2 of t. Okay, and then you know that this is some function shifted, and we need to figure out what was the unshifted function. So we will do some manipulation. Okay, so since the unit, the c is 2 here, we would like to express this here and as a function of t minus 2. So if we put it in t minus 2, then we need to plus a 5, so this will still equal to t plus 3. Okay, so therefore we write it like that. Okay, and then here I can break it into two terms, or I don't really have to, but let's do that. So I have u2t times t minus 2 plus a 5 times u2 of t. Okay, now I'm ready to take Laplace transform of I can transform of the first one here, and then take the transform of the second one here. Okay, so this is also a easy example where the manipulation is rather simple, just this manipulation. And then here we can recognize this is uc of t times a g of t minus c. Here c is 2 and gt, where you change the t minus 2 into t. So that's just t. Okay, and then you can apply the shift theorem for this part. With this, we have done it already once this is figured out. And then the Laplace transform of the step function, which we already know, we can put it in. Okay, so this gives us e to the negative 2s, that's the 2 here, times the Laplace transform of t, which is 1 over s squared. And then 5 times the Laplace transform of u2 is e to the negative 2s times 1 over s. Okay, so let's take one more example, which involves a bit more manipulation. So the function here, call it gt, is 1 on 0 to 2 interval, and then for t bigger than 2, it's t squared. Okay, so let's write it using step function. We could use the quicker algorithm, that is, we take 1 here, starting from 0, so we have a 1, and then we look at the point that it's discontinuously defined, that's 2, so we have a u2 of t, and this is multiplied by this function minus that function, so t squared minus 1. Okay, so you can actually directly write out here, and you can skip this step. Now, this is 1, it's okay to take Laplace transform, but this is multiplied by the step function. So we want to view this as a shifted function. That is, for the function that's given here, we want to write it not as a function of t, but as a function of t minus c, where c is 2. Okay, so here is a manipulation one can do. So t squared minus 1 equals, so I don't want t, I want t minus 2. So let me put down t minus 2. But then it's wrong, right? So then I would add a 2. Okay, so then that means I add 0, so this equation holds. And now I treat t minus 2 as a unit, and then I expand this unit plus 2. I expand the square. Then I get t minus 2 square plus 2 times 2, 4, t minus 2 plus 2 square, 4 minus 1. Okay? And then the 4 minus 1 can be computed, and you get 3. Therefore, it will take this form. Okay, so putting this back, then I see that the g can be written as this. So the tricky part now is to, this part is a shifted function. So we need to recognize what is the shift and what is the original function. Okay, so you can think this is uc of t times some function f of t minus c. What is the value c? Well, c is 2, right? And then what is the function f of t, the unshifted one? Well, that wherever you have t minus c, that is t minus 2, you will replace those with t, right? So this will give me t squared plus 4t plus 3. Okay, so then the Laplace transform for this part will be the exponential function e to the negative 2s times the transform of this ft, which is t squared plus 4t plus 3. Each term we know how to transfer. Okay, so we can write this out now easily. Okay, so therefore we see that Laplace transform is the transform of 1, which is 1 over s. E to the negative 2s comes from this. And then the transform of the shifted function, so t squared, which is 2 over s cubed, 4t, which is 4 over s squared, and then 3, that's 3 over s. Okay, so that is the answer. Okay, so let's take one more example just to get really comfortable with this procedure. So here we have a function which is 0, basically which is 0 outside the interval from 3 to 4, and on the interval from 3 to 4 it's e to the t. Okay, so we need to rewrite it in terms of the step function, and then we can just take et times the rectangular wave that picks up this interval. So u3 of t minus u4 of t. Okay, and now we can distribute the e into each of this step function, and then we'll have a et times u3 of t. And if we want to treat this as a shifted function, then we would rather like to write it as a function of t minus 3, right? So if we do that, then we'll have to multiply it with a e to the 3 to get the same function. Okay, so this is what you will multiply with u3. And then for the term with u4, you would want to write the function as a function of t minus 4. So that's what you put there. And then you need to multiply with the e to the 4, a constant. So this will still be e to the t. Okay, so let's think this is, just write out take our steps. So we think this is uc of t times a g of t minus c. So what is the c here? C is 3. And what is the function g of t, the unshifted one? Well, it will be e to the 3 times e to the t. You will change t minus 3 back into t, right? And then for this function here, let's say this is u of c of t times, let's call it h of t, just the name of the function. We used f and g, so. And then here c equals 4. And what is the unshifted function here? Well, it's e to the 4, which is a constant, times e to the t, where you take the t minus 4 and change it into t, shift it back. Okay, so with these written, then you just simply apply the shift theorem and take the Laplace transform, the second shift theorem. Okay, so that's what we do. So applying the second shift theorem, so here u3, the shift, give you the exponential term here. E to the 3 is a constant, and then e to the t, the transform, is 1 over s minus 1. Okay. And then for the second term is the same, and the shift here give you e to the negative 4s, and then we have e to the 4, and then e to the t, the transform is 1 over s minus 1. Well, if you like, you can take out 1 over s minus 1 as a common factor and collect the exponential functions in this way. But you don't have to. Okay, so that's the last example I'm giving in this video on taking Laplace transform for piecewise continuous or piecewisely defined function by using the step function and the second shift theorem. Okay, I hope this is useful and I hope you enjoyed it. And next time we'll look at the inverse Laplace transform involved with this originally discontinuous function. Okay, so hope you enjoyed this video and I'll see you next time.